Okay, thanks, Mike. Okay, thank you. So it's great to see everyone here. So on behalf of the whole Axis team, it's a huge pleasure to be able to kick this session off by giving you just a very brief overview of Axis. I'm not going to talk very much about the science talk. I'm going to leave that to the science team who will come and speak after me. But I wanted to give you just a round overview of what Axis is and briefly sort of how we're going to do it. Now, just to sort of set the scene, it is it's not working, Mike. Oh, there we go. Okay, great. So it is almost 24 years ago that Chandra launched. It's I think it's that long. And of course, Chandra, it opened up the world of high spatial resolution X-ray astronomy, which really let X-ray astronomy now be relevant for things much more, for basically every part of astronomy and astrophysics, not just those that were traditionally part of X-ray astronomy before. So this is just a set of results from Chandra. I won't go through these. You can probably see your favorite one up here. Of course, we've got deep fields, we've got galaxy clusters and feedback. We have, the Eagle Nebula and star formation. We've got even planets, Jupiter and Mars over there. So this is just to show you that just the reach of high resolution X-ray imaging. So this is the motivation for the Axis concept, and we sort of started thinking about this pre-decadal survey in 2017. This is the picture of the first kickoff meeting of Axis. And at the back there, you can see, and the resolution, ironically, of this pointer is not very good. But at the back, you can see Richard Moshotsky, who is the PI of Axis in the pre-decadal concept, and also Erin Kara, who is now the deputy PI of Axis, and is sitting on the second row here. So in a nutshell, what is Axis? Axis is a high resolution, so a 1 arc-second class, large collecting area, large field of view X-ray emissions. So these are the basic parameters of Axis here. 1 arc-second resolution on Axis. I don't like that point, so let's not use that. And 1.5 arc-second resolution field of view average, 5,000 square centimeters. To put that in context, that's 10 times Chandra. That's 10 times the collecting area of Chandra when Chandra was launched. And of course, Chandra's had contamination degradation since that point. And then the other aspect of Axis is we are in low Earth orbit, which means low background in our fields. We do low surface brightness astrophysics and good communication. So Axis will have a fast transient responsibility part to it. We can get, once we're given an alert, say a gravitational wave source or just be localized, we can get on target within 2 hours. And then we also will have onboard transient detection, and if we see something flash in our field of view, we can get those coordinates and the basic data down in 10 minutes for dissemination to the community. So compared to Chandra, for example, that one important thing is that we have a very, very graceful degradation of our point spread function across our large field of view. So you can see that in this plot here. And the risk of doing this again. So the optical design of our instrument means that from being on axis until quite far off axis, we have a very, very slight degradation of our PSF. So we have good resolution across our whole field of view. Just to briefly mention our partners. So I'm at University of Maryland, the PI, Erin, deputy PI, and also our focal plane array leads are at MIT. NASA Goddard is our lead NASA center on this, and is also responsible for building the mirror assembly, for delivering the mirror assembly. Northrop Grumman is now our spacecraft partner, and also working on our metrology. And then we also have Penn State and Stanford, our key players in the electronics of our system and our detectors. And then we have a partnership with the University of Erlangen in Germany for our simulation software. Okay, in the heart, a critical piece of our system is the Axis mirror assembly. It will be the most beautiful X-ray mirror ever built. And so at the heart of that is this monocrystalline silicon technology. So we have these monocrystalline silicon shells that are carved out and polished, coated with iridium, stacked up into these modules, these sort of bricks, and then we have 300 and something, or 312 of these modules that will fill out our array. So this whole thing's a little under 2 meters diameter. This is then held into what we call the spider, which is the frame that holds this whole thing together. And then you pack that up with your necessary, thermal pre and post collimators to keep the mirror nice and toasty and warm, and then put that in your nice silicon shell. And that's our mirror assembly. That's how we'll achieve that. As has been pointed out already by the previous probe talks, so both Hexby and Lem pointed this out. By mandate, 70% of the observing time of in the probe is going to be general observer time. So this is how we see our time breaking out. We will have, even though in low Earth orbit, because we have fast slew capabilities, we have Swift-like slew capabilities, we actually can maintain our observing efficiency to at least 68%. So it's significantly higher than the usual 50% you think of when you're in low Earth orbit. And so with that baseline, we have the Axis science team's time is about 34 megaseconds, and then the rest of the observing time, something, 81 megaseconds is general observer time. And our guess is that this breakdown between TOOs and targets, but it doesn't really matter. It's up to the general observers what they want to do with that. This is just an example, or this is our so-called science traceability matrix, and this gives you a view of the breadth of our science. Okay, so Axis will have impact across all 3 pillars of the decadal survey, both the cosmic ecosystems pillars, the world and suns, and the new physics and new messengers pillar will have impactful reach across all pillars. And some of our key science, just to flag some of this, and we'll hear about some of this later. In our medium and deep surveys, we will be able to quickly flash off that before let's go to that. In our medium and deep surveys, we will be able to get thousands of AGN. In our deep survey, we can get about 3,000 AGN. In our medium survey, we can get about 30,000 AGN. Many of those will be high redshift AGN, and we can start to really address the question of whether there are massive black hole seeds at a redshift of 8, 9, 10, of the kinds that very, very recently Webb is starting to suggest are there. We'll be able to look at how black holes grow over cosmic time by looking at, for example, joule AGN, an idea of black hole mergers from joule AGN. Sort of skipping down towards the bottom of this matrix, we'll be able to look at the stars of exoplanet hosts and get exquisite information on just how X-ray active the hosts of exoplanets are. Looking at that compared to what we'll learn about those exoplanets from Webb and future ELTs, we'll be able to correlate what we find about the X-ray activity of hosts with the chemistry of exoplanets, therefore get a handle on the habitability issue. And then, as I mentioned, we are a capable observatory for the transient science, and so we will be able to study supernova shock breakouts with our transient alert. We should be able to detect hundreds of supernova shock breakouts and follow up, for example, LIGO sources, but in fact follow up any kind of transient sources that are coming from Rubin, from SKA, from any other sources. So these are our 5 science working groups that we have, and we're going to hear from representatives of each of these science working groups in this session. But I just want to sort of flag and give a shout out to the co-leads of these groups who have been putting in a truly colossal amount of work, all volunteer, of course, in corralling our science case together. And at that point, let me wrap up, and I have time for a couple of questions. Before I do, I want to point out that you can get your latest fashion accessories from Axis. Wonderful Axis pen that is there's some at the back, and we'll leave some out at the end of the session. Axis pin, which you probably can't see here, but nice and shiny, and very nice Axis stickers that are a great bag. You can identify your suitcase with these by sticking on your suitcase. So that's all at the back to remind you of how great Axis will be. And at that point, let me stop. Thanks.
Okay, great. Do we have time for a question or two, or we can go directly to the science? Do that, Annie. Tell us about AGN surveys.
This progresses the slides. Okay, great. All right, hi everyone. So my name is Foord. I am co-lead of the Axis AGN Science Working Group. Nico Capellini, who's also in the audience, is the lead. Feel free during this conference to come up to any of us if you want to chat more about AGN Science with Axis. So today I only have a few minutes to give you an overview of some of the really exciting science that we can extract from these high Z AGN surveys that we hope to carry out with Axis. And as Chris mentioned, the power of Axis is its really large field of view, its really stable PSF, and its excellent sensitivity. And those three things combined are really going to revolutionize our understanding of supermassive black hole growth and evolution over cosmic time. Okay, so as of right now, quasar progenitors and early QSOs are still missing in many serendipitous surveys. So here I'm showing many X-ray surveys that have been taken in the past, including CDFS and the Chandra Cosmos legacy. And what I'm overplotting here are the sensitivities that we can reach with two different fields, an Axis deep field, which will be about 5 megaseconds, and an Axis intermediate field, which will be about 300 kiloseconds or so. And as you can see, with the Axis deep field, we will be sensitive to fluxes on the order of 10 to the negative 18 per second per centimeter squared. And this is much, much lower than what we are currently able to do, and will really revolutionize the field of understanding where these high Z AGN are. So this is a figure showing potential Axis detections from surveys, as I mentioned before, and plotting their X-ray luminosities as a function of their redshift. And we're also overplotting two different scenarios, assuming a light seeding scenario shown in the orange line and a heavy seeding scenario shown in the pink line. And as you can see, different seeding scenarios predict a different number of AGN as a function of their X-ray luminosity and also as a function of their redshift. So the more AGN that we're finding as a function of higher redshifts, the better we have of understanding how these supermassive black holes possibly formed. And in general, the evolution of luminosity functions can really help constrain seeding and growth models. So these are showing results from semi-analytical models that tracked the growth of supermassive black holes, prescribing various accretion modes and assuming different seeding scenarios. And what you can see is that the heavy seed scenario, the heavy seeding scenarios in general predict more luminous AGN, and the light seeding scenarios predict more or less luminous AGN. And what we're showing in a dashed line is a hypothetical limit for an Axis deep field. And so the idea is by finding more high redshift AGN, we'll be able to have unprecedented fine tuning on a lot of the different seeding models that exist, and perhaps even be able to exclude certain regions in parameter space when we're trying to better understand possible seeding scenarios for all of these supermassive black holes. Okay, another really big question that Axis is going to give us a lot of insight on is how do supermassive black holes grow? And the axis fields will yield some of the most tightly constrained measurements of the evolution of dual AGN across cosmic time. So this is a figure from a paper that carried out a theoretical analysis of the growth of supermassive black holes as a function of their redshift and a function of their mass. And what they found is that for supermassive black holes, in the earlier universe, their growth was perhaps accretion dominated, while in the later universe, their growth was perhaps merger dominated. And so because dual AGN tracks galaxy mergers, understanding how the rate of dual AGN evolves over cosmic time will give us a lot of insight into the different environments of the universe and how that affected the supermassive black holes that were growing then. So as of right now, there's no really well-constrained measurement of the fraction of dual AGN across redshifts, so we don't really know what to expect. These are results from various hydrodynamical simulations shown in the purple and in the green. And then we also have a nearby constraint that you can see is much higher than what the hydrodynamical simulations predict. But as of right now, we don't really know what to expect when it comes to what the dual AGN fraction should be as a function of cosmic time. And what we're currently trying to do is measure this using various deep and wide Chandra fields. And so we're currently analyzing hundreds of AGN that exist in these Chandra fields and trying to measure what the dual AGN fraction is. A lot of these have redshift measurements because they cover complementary fields from other wavelengths. And we're getting stuck because of the off-axis angle of Chandra. So we're finding that once you reach off-axis angles around 3 arc minutes or more, it becomes really hard to find a dual AGN because the PSF is just naturally extended in that region. And what I'm overplotting now on this figure is the predicted dual AGN fractions just from our Chandra samples. So the best that we can do, assuming one of those hydro simulations is correct. Axis is going to be finding tens of thousands of AGN in just the deep and intermediate fields that I spoke about. And because of that, our error bars are going to be much, much smaller for all of these dual AGN fractions. And the most exciting thing, I think, is that we're going to start to push our measurement to higher redshifts. And I want to highlight that this is just using the deep and intermediate field data from Axis. We also should have a lot of data from just geo programs. And it's possible that we can push this out to even higher redshifts. And this is where it gets really interesting in redshift space. Where models start to predict that the growth is either turning over from merger dominance to accretion dominance. And I think that that's all I have. Yeah. So thank you very much.
Okay, so any questions for you? So I'll ask you a question about dual AGN.
Yeah.
So most of these are obscured, right? So how does this compare to the sort of distant dual AGN that is finding?
What are the predictions?
So how would it be so different at like population based on astrometry?
At local universe or?
No. I'm speaking more of the sort of distant duals that have been detected based on the astrometric.
The varstrometry or whatnot? Yeah, I mean, so the varstrometry is sensitive to closer separations, right? Because you're not directly detecting emission there. And so I think that what the sample that the varstrometry is looking at will be different than what Axis is sensitive to. We're not going to be sensitive to those really small physical scales. But that being said, it'll be super complementary. So it might be that via varstrometry, we can try to target a population that's different than what Axis is sensitive to. Yeah.
Great. Any other questions? Okay, well, let's go on to the next talk on transients.
All right, thank you for attending, everyone. I'm Mark Reynolds. I'm part of the time domain working group, and I'm going to tell you about some of the things we've been thinking about doing with Axis. This is the sample of people who've been involved in thinking about this work. The leads here are Brad Chenko and Daryl Haggard. And if you're interested in doing time domain work with Axis, please get in contact with us. So the driver here is the decadal survey, and in particular the TDAM area and the new windows on the dynamic universe. And Axis is going to make great impacts here. Now, one of the things that's happening as we move into the next decade is that our current fleet of missions are aging, and so there is this discovery space present in time domain land, and Axis can fit in here and complement the radio, optical, and multi-messenger facilities that will be available in coming years. And we really need to think about how we advance our ability to do observations, because, for example, here are plots from gravitational wave land, and we're going to see with LIGO Plus, by 2030-ish, they're going to start pushing out tens of neutron star mergers per year. And we'll be looking at hundreds of black hole mergers. So we need to think about how we will follow these up. There's lots of physics going on here. And so the plot on the left here is the neutron star merger. And so we have the nucleosynthesis occurring, and then there's the relativistic jetted emission. And this is allowing us to probe things like general relativity, the equation of state, and everything up to jet physics. Now with Axis, we're moving from where we are right now to say a trigger from LIGO of maybe 1 per year up to by to 2030 window, maybe tens per year, and plans to go to hundreds there afterwards. Now they're still on the drawing board. So that's what we need to be able to tackle. 170817 is in the plot there. And so you can see with Chandra, there's a gap in sensitivity coverage at early times, and Axis response and slew rate will allow us to get on and probe that region of parameter space. And then at late times, Chandra is, its effective area is now starting to not be able to collect enough photons to really probe much lower in the evolution of that source if it keeps decaying. Axis will dramatically improve our ability to do that science. There's multiple other things we've been thinking about with LISA. The plot here is showing the signal to noise you get for supermassive black hole mergers, going in red from thousands up to very, very high redshifts where you're still getting signal to noises of 10 to 20. The number we want to think about is something like 10 to the 6 solar mass black hole at a redshift of 6. Accreting at Eddington is about 2 times 10 to the minus 16. So in Axis observations, we'll be able to go and chase after the fields where LISA says there are mergers happening and measure electromagnetic signatures. And it's the electromagnetic signatures then will allow us to place these gravitational wave signals in an astrophysical context. Chris mentioned supernova shock breakouts. At the moment, the massive stars are about half of the supernovae sample, and we have very limited observational constraints. Plot here is showing sort of time from explosion, going from, say, 10, 100, 1,000 seconds for different classes of massive stars. And so its rapid response at early times constrains these curves. These are theoretical. We do not have good observational constraints. Axis will be able to do that. And we think that we'll get hundreds of these sources over the nominal mission lifetime. Quasi-periodic eruptions are an AGN phenomena that have really only been revealed in the last few years. It's some sort of periodic behavior in the accretion flux. There's various explanations, ranging from disk instabilities to TDEs. They're poorly understood right now. Axis field of view and its sensitivity will increase this sample, and we think we'll be getting tens times greater than what we have now, really changing how we can understand these. TDEs will be another area where access will be really beneficial. We can use combinations with, say, Rubin, and here the idea is to compare the X-ray and then the UV, the alpha OX parameter, and that's telling us what the SED is doing, and that's giving us constraints on the mass accretion rate and the accretion flow configuration as this star is disrupted. And we think with sort of a combination of Access and Rubin, we'll get to thousands of objects to populate plots like this and really be able to figure out what's going on. Fast X-ray transients are a sort of much more mysterious object. They've been seen in Chandra observations. These are very short seconds scale events, rapid increases, rapid decays, and their origin is currently unknown. Access large field of view and sensitivity will give us orders of magnitude more of these events, and you know, cross correlations with other wavelengths then will allow us to really figure out what these are. So there are of course many other things we can do, from changing look AGN, magnetized X-ray binaries, fast radio burst follow-ups to see if we can find X-ray signals, gamma ray bursts, exoplanets. And basically what we want is anyone here who thinks that they could do good things with Access, please get in touch. We're really interested in hearing what happens. And as Chris emphasized, there's going to be a really vigorous GEO, DDT, TO program. And so time domain science will be a really good thing to do with Access. Thank you.
Okay, questions?
Nice talk. I'm curious how you get order of 100 per year on talk breakup in your star different observations. Is there kind of volume limited, or because up to 20 megaparsec or something inside field deep for Access, you could expect maybe 1 to 5 years. So I'm curious how you come up with that.
It's not purely from serendipitous observations. It will be from follow-ups of events that are being discovered in optical and other surveys. And so the idea is we get there early with our sensitivity, and we can do it.
Thanks.
Okay, what questions?
So going on the short breakout, how hard is the 0.5 KV limit? We've got some studies from theory to short breakout, and they keep more like a 0.1 KV. So the number of events we predicted to see go 0.5 KV drops considerably from 0.1 to 0.5. So I'm hoping that quickly will push down on that lower limit.
That's something we will have to work at in our simulations. But the telescope is sensitive down in those regions, and it has large effective area there. So we think we will be sensitive to that type of physics.
Yeah, Eric's going to talk about that as well. Yeah. Other questions? Okay, if not, let's go to the next speaker.
So just forward backward and hop on the spot. Great. Thank you. Hello all. Yes, I'm Anthony Flores, grad student at Stanford and member of the Access Galaxies Science Working Group. Most of my work focuses on galaxy clusters and how we can use X-ray observations of them pushing towards the highest redshifts. But given that I'm speaking on behalf of the entire Galaxies Working Group today, I did just want to make sure I took a second and discussed kind of the broad span of galaxy and galaxy cluster science that will be enabled with Access and how far-reaching it is. There is a great poster on this 102.30 that highlights a number of science cases included but not limited to stellar feedback. So looking at the interplay between stellar feedback processes and the hot interstellar medium, feedback from X-ray binaries, and trying to resolve gas flows on the kiloparsec scales. Looking at AGN feedback in individual galaxies, shocks and gas outflows from, for example, massive ellipticals or Seyfert galaxies, and trying to see if galaxy cluster scale feedback truly does scale down to the galaxy level. Being able to use AXIS to look at the defined structure of galaxies and galaxy clusters and how they interface with the structure of the cosmic web and the connections there, and my work in high-Z clusters. So take a look. I encourage you all to engage with the broad swath of galaxy science possible with AXIS, and take a look for the absolutely beautiful purple color map of the cosmic web when looking out for posters. But in terms of high redshift cluster science, AXIS will reveal the profound role that AGN feedback plays in shaping the observable universe in multiple ways. First, it will reveal the instantaneous effect that AGN have on the state of clusters. For example, how AGN heating and jets can produce massive cavities in clusters, for which we can probe the dynamical state. And additionally, seeing how AGN feedback contributes to the integrated history of feedback and evolution of a cluster up to the redshift at which we are observing them. And so we can see this in how AGN feedback affects the thermodynamic profiles and the chemical history of clusters. And while current studies, mostly using Chandra and XMM-Newton, are essentially limited to redshifts 0.5 to 1 based on sensitivity and spatial resolution, AXIS will enable us to push these studies to redshifts of 2 to 3, fully encompassing the period of cosmic noon where we expect these feedback processes to be most prolific. One specific science case that I want to highlight when looking at these studies is metallicity and the early enrichment scenario. Looking at local clusters, low redshift measurements of cluster outskirts using Suzaku, what we see are an approximately consistent and constant level of metallicity, both within an individual cluster and from system to system. And when we extend these measurements of bulk metallicity out to higher redshifts using Chandra and XMM-Newton, we see little to no evolution or evidence for evolution in this bulk metallicity, pushing towards and just past a redshift of 1.5. And one of the ideas here is that early periods of star formation paired with intense periods of AGN activity is responsible for enriching the early universe. But if we truly want to answer how and when this enrichment occurred, we need X-ray observations of galaxy clusters spanning this high redshift range, encompassing cosmic noon. In addition, you may ask, well, what clusters are we actually going to observe to answer these questions? And this highlights the synergies of an observatory like AXIS with current and upcoming SZ surveys, Sunaya-Zeldovich surveys, which are currently our best way of detecting massive high-Z clusters. And as evidenced by this plot on the lower right, while we really only have a handful of high redshift clusters, particularly those with X-ray follow-up, the South Pole Telescope, Atacama Cosmology Telescope, and Simons Observatory are going to greatly increase the population of massive clusters at redshifts of 1.5 that will be primed for X-ray follow-up with AXIS. And essentially, if you extend this plot backwards, what you would see is that Chandra and XMM together provide great insight into the cluster population at redshifts of 0.5, but quite sparse coverage at a redshift of 1, essentially being limited to the brightest, most massive systems because of how expensive it is to get measurements with current telescopes. But AXIS will provide precise measurements of individual and ensemble properties, density, temperature, metallicity, out to a redshift of 3, routinely being able to make the measurements that we need to probe feedback history in the universe. And so we've developed an observing program using AXIS that targets 40 clusters at 100 kiloseconds each for a total of 4 megaseconds, with 10 clusters each at redshifts of 1, 1.5, 2, and 3 to get a broad picture of this evolution. And we're allowing ourselves to be flexible here because while we don't truly know the extent of the upcoming cluster catalogs from these SC surveys, we expect that these clusters are going to be representative of the most massive X-ray luminous systems at these redshifts that will be primed to deliver the most interesting physics to us. In the interest of time, I won't go through the entire technical details of the simulations we've been doing with AXIS, but I just want to emphasize that AXIS uniquely provides the combination of spatial resolution, sensitivity, and low particle background that allows us to simultaneously resolve density and temperature in cluster cores and metallicity extending through cluster outskirts, which is something we have not been able to do before. Looking at the results of these simulations in a bit more detail, the current simulated AXIS responses give exquisite precision in temperature profiles for hot clusters out to R500, as you can see here. Oh, excuse me, on the left, and still better than 10% precision all the way out to twice R500, approaching the virial radius for higher redshift systems. Looking towards similar constraints for metallicity, current responses yield about 10% precision in metallicity profiles for redshift 1 massive clusters, and better than 40% precision as we extend towards higher redshifts. And if that doesn't sound like an immediately impressive figure, I want to stress that that means that 100 kiloseconds of AXIS data at a redshift of 2 is going to be more constraining than 500 kiloseconds of joint Chandra and XMM data at lower redshifts. In particular, that means that these measurements of cluster metallicity are primed for us to combine them in a statistical ensemble. So this plot on the right is essentially zooming into the outskirt metallicity figure that I was showing earlier, with the blue points and constraints representing the best constraints to date we can make with Chandra and XMM, totaling 1 megasecond of data. And the red points are what we are able to constrain metallicity evolution to using this projected 4 megasecond AXIS program targeting the 40 most luminous, most massive clusters between redshifts of 1 and 3. And so this means that AXIS not only constrains the mean evolution of metallicity, but also provides a good estimate of scatter from system to system in these high Z clusters. Because remember, each one of these data points actually represents 10 clusters combined in statistical ensemble. And this dramatic increase in precision will allow us to clearly discriminate between models of chemical enrichment in the early universe, both the shape of the models we actually use and actually allowing us to verify the early enrichment scenario. So I will end there. I am always happy to talk more about high redshift clusters. I especially encourage you to engage with the broad variety of galaxies science that's enabled by AXIS. And I hope I've impressed upon you just a little bit on the power of an instrument like AXIS in providing information into the evolution of these systems across cosmic timescales.
Okay, so question. I'll actually ask a question when people are thinking. So I could imagine you could also, with the great spatial resolution, get some information about like cluster cavities that might give you a different sort of line of understanding of what's going on with feedback. How do you think about that? In addition to all the great information on sort of the temperature and metallicity.
You mean in just the sense of what AXIS can provide, or?
Yeah, different options.
Yes, so cavities are going to be more difficult to measure than thermodynamic and chemical profiles, but AXIS absolutely will be able to resolve the cluster cores and give us those imaging analyses where we can see those cavities. It's likely going to be based on targeted follow-up of clusters that potentially exhibit those cavities, because depending on the strength of the jets or the outflows that produce them, that is going to be explicitly relevant to how difficult they are to resolve. But yes, with that spatial resolution in the cluster cores, AXIS is essentially the only instrument that's going to be able to resolve that physics.
Okay, great. Any other questions?
So my question is what is iron balance for us, right? So people might go to the iron typically you average out like limited huge panels fail in the region. With that, you measure your average out all these spatial variations. Would your point or goal would be to actually measure smaller regions, and is it possible like how small regions would be possible to measure less simulation to that?
Yes, so I will say one of the typical results we're getting from lower redshift is that outskirt metallicity is azimuthally consistent. So we don't really expect there to be great variations in different regions past a certain spatial extent. That said, the spatial resolution of Axis is going to be able to potentially, yes, resolve different pieces of cluster outskirts. But let's say for a cool-ish, not cool core cluster, but a redshift 3 cluster with a peak temperature of about 3 to 4 keV, R500 is approaching 25 to 20 arc seconds. So being able to resolve those distances might be able to give us a few bands in azimuth, but even then it's going to be difficult. That said, Axis is certainly the only instrument that's going to be able to do something like that in the outskirts of clusters in that sense.
Okay, great. So let's switch to something a bit smaller. Stars and exoplanets.
Thank you. Hi, everybody. I'm Rodolfo Montez. I'm giving this talk on behalf of Mariana Kunkel and as a part of the Stellar and Exoplanet Working Group, which I have their names up here. And if you know any of these folks, you know that this is quite a variety of science background and expertise and interest. My own are also not going to be reflected in this talk, but we have talked quite a bit in our working group about the broad range of science that we can do with Access if Access is successful. I particularly am interested in evolved stars. I'm interested in planetary nebulae and the very soft plasmas that occupy their optical cavities, and that we really need the high spatial resolution and soft sensitivity that Access will provide to study. We've also talked about objects in our own solar system like Jupiter, which is an experience interaction with our sun through its coronal emission that you can detect with the soft sensitivity of an instrument like Axis. The talk that I'm presenting today is focusing on this decadal theme of the worlds and sun in context, and essentially addressing this particular question here, which is how does stellar activity affect the evolution and habitability of exoplanets? This is identified as one of the key problems that we want to tackle in the coming decade. And I want to just take a step back to remind you all, when we do finally get an atmosphere measurement of an exoplanet, that's just one piece of the puzzle. The larger framework of how habitability evolves is it's gonna matter how those stellar environments start off. It's gonna matter how stellar activity will impact those planets as they form. So I'm showing here a very complicated diagram showing you some of the different components that go into understanding habitability and exoplanet habitability in particular. And I've highlighted here the part that I'll be talking about, which is that stellar activity. And so when stars are born and they're very active, they're producing a lot of high energy radiation, and that radiation has the potential to actually evaporate or ablate the atmosphere from a newly forming exoplanet. And so understanding that in context of the whole question of exoplanet habitability is an important part for studying exoplanet habitability. I have here a little artist's illustration of a planet whose atmosphere is being ablated. So in addition to that, we're all familiar with our G star sun and our own habitability. I'm showing you here a K-type and a M-type stars, and I'm showing you how much their X-ray radiations, how much their habitable zones, and the relative number of those stars changes as you go through these different scales. So if you're in a K star, your habitability zone is a little bit smaller. And so you're experiencing a lot more of that X-ray radiation, 25 times as much. And there's maybe like 3 times more K stars than there are G stars in the studies that we're thinking about. And then when you go to M stars, that's an even smaller habitable zone. And this is where most of the planets, exoplanets, are going to be found, or have been found, or projected to be found, I should say. And there you're experiencing 400 times the high radiation environment that we would experience around a star like our sun. But you have a lot more of these objects. So really, you're going to see, if you have the sensitivity to detect these X-rays around these M stars, you're going to see a lot more of that environment. Here's a model diagram showing you the age on the y-axis and the effective temperature of the star on the x-axis. And it's color-coded by the spot size fractions, so the fraction of the surface of the star that's covered with spots. And you can see that dark color is a higher fraction, and these faint blue, fuchsia, white-ish colors, where the main sequence is where the star spends most of its life, it's a very low spot coverage fraction. But when you're young and entering the main sequence, you're experiencing a lot more spots on your surface. In addition, we know from studies, but only a few studies, that the X-ray emission is a function of age. And so when you're young, you have a very bright X-ray luminosity. As you start to age, that decreases. This X-ray luminosity age relationship is really only based on a few clusters where we have the data to actually determine what those X-ray luminosities and ages are, because you need a cluster to get a really strong age from that. So we don't have that many clusters where we have the X-ray depth to actually detect and characterize the X-ray flux. This is the Chandra-Orion Ultra Deep Field. This was almost a megasecond, a 13.8 day exposure of the Orion Nebular Cluster, covering a range of X-ray luminosities. It's one of the early amazing projects that Chandra conducted. And I'm just showing you this image here, which is color-coded by the energy of the X-ray photons. And I want you to notice that on the outskirts, you have these blobs, and those blobs are because of the PSF decreasing. This is ACES I, so this is about 16 arc minutes on a side. There's 4 chips in there. And in the center, you have really nice crisp images. And that's really the power that Axis is bringing to this field, is because of the good PSF resolution at high off-axis angles. You don't suffer from this broad PSFs that can obscure sources in a very crowded field. You wouldn't be able to discern if there were a few sources in those blobs or just one source because of that PSF. And I'm going to remind you now, I forgot to set my timer, so please, if I'm going too long, let me know. This is the star forming region that we were just looking at, but the part we're actually looking at is labeled right there in the lower center, ONC. That's the Orion Nebular Cluster. And so that little pink blob down there is this region here. This is the actual field that I was showing you from the COOP study. And so you can see it's a very small field. This has problems because we're looking at this dense region, and the environment that those stars are born into is going to impact the stars themselves' evolutions. And so all the conclusions we draw from things like this are potentially biased unless we have a broader view of the entire nebula and star forming region and all of its stars. And that's really what we're going to be able to do with Axis. We'll be able to do this with 20 times the sensitivity of Chandra, and we'll be able to observe many more stars. And my poster is 16118. And in that poster, I have simulations of the Carina Nebula showing you what we will be able to do with the stars in that nebula from just 150 kilosecond pointing of axis, whereas Chandra's images of it took about 24 mosaics to cover the same region that we're talking about. And we'll be able to actually go much deeper in 50 kiloseconds than that mosaic could. So in summary, AXIS will enable characterizing stellar activity with age. It's a key ingredient for understanding the frequency of habitable planets in our universe. It'll characterize flaring of these objects. It'll also shed light on the origin of the scatter in the age luminosity relationship, which if you come to my poster, you'll see the scatter that I'm talking about, especially in the saturation regime. And we'll be able to disambiguate additional physics that's happening to cause that scatter in that age luminosity relationship. And then we'll also have synergies with other large surveys in stellar astrophysics. And that's all I have. Thank you.
Great. So are there any questions? Okay, maybe let's actually, just because we're running to the end of our session, we'll go on to the next set of speakers and we'll have a few minutes at the end. Hugh Yang and Noel. Or actually, Vegas. I'm just kidding.
Please, okay. Aloha, and I'm Hui Yang, and I'm a graduate student from the George Washington University. I will be presenting for Noel and Jeremy, who unfortunately cannot be here today, and on behalf of AXIS, I'll be talking about compact object and supernova remnant sciences with AXIS. And so in the first part, I will be talking about the supernova remnant and pulsar wind nebula prepared by Noel. And since the launch of Chandra, there has been about 100 X-ray pulsar wind nebula discovered due to the Chandra's high resolution and excellent collective sensitivity. And AXIS will revolutionize the pulsar wind nebula science in many ways, but in this talk, I will focus on two of such areas in such a short talk. And spatially resolved spectral maps is a powerful tool to understand how electron photon index gamma evolves with time and distance from pulsars. In the upper plot here, shows the spectrum maps which reviews the spectral anisotropes, which we can only see the isotropic spatial distribution from the Kant's map. And in the middle panel of the spectral map of Vela, we can see the spectral reheating away from the pulsar, and where the particle reaccelerated. And this applies to some other sources here. And with population studies, we can have a better understanding of wind ejection spectrum and the particle acceleration mechanisms. However, there are only about 10 pulsar wind nebula that are bright enough for such a studies. And for the faint and older pulsar wind nebula population, it requires exposures up to 1 megasecond from Chandra for such a study. And with AXIS 10 times better effective area, we will be able to triple the sample of such a mappable pulsar wind nebula with typical exposures of about 100 kiloseconds. Another interesting science case is misaligned outflows that is discovered which is shown in this green ellipse here, which is these kind of weird structures that are strongly offset from the pulsar's velocity, which is shown in the magenta area ellipse circles. And this kind of weird phenomena has only been discovered in the recent 15 years, and it can only be detected by Chandra with hundreds of kilosecond observations. And with access exponential sensitivities, we will be detecting much more of these misaligned outflows with tens of kiloseconds instead of hundreds. And also it is with Chandra's great angular resolution, we are able to resolve the arcsecond scale structures, which shown here, which provide a great insight into the rich physics of this kind of phenomenon. And it highlights the needs for access to have also such arcsecond scales, and so for us that we can to resolve these structures and to get full pictures. And for the second part, I will be talking about the galactic plane survey and the globular clusters prepared by Jeremy. And access will enable efficient and deep surveys, including the galactic plane survey. And so the obvious advantage of access compared to Chandra and the eROSITA is its high efficiency and the excellent angular resolution across the field of view, where the Chandra's the PSF degrade rapidly with larger off-axis angles, and it is important to accurately locate the location of the faint X-ray sources detected in such surveys, and which will allow us to find the multi-wavelength counterparts and with the multi-wavelength counterpart combined with the X-ray properties, then it's become possible for us to identify the nature of these faint X-ray sources. And the exact galactic plane survey strategy is still being actively discussed, but I will present 2 iterations of how such a survey will look like. And the first strategy focuses heavily on the 50 degrees in longitude near the galactic center. And the majority of the exposure will be spent, we'll have about 5 kilosecond exposure reaching to the flux limit shown in red, and a deeper exposure of about 20 kilosecond will be with a 3 times better flux limit will be spent on bulge and normal areas, with an even deeper pointing of 100 kiloseconds spent on the galactic center, and the total exposure will be about 9 megaseconds. And this survey will enable to unveil the hidden source population and to access the contribution of faint pulsars to the diffuse X-ray background and 511 kilo EV emission. And it will also allow us to study the number flux relations for the source population, including magnetar and high mass X-ray binaries. A possible second galactic plane survey will focus on uniformly sample the whole galactic inner plane, and with 2 kilosecond pointing reaching to a flux limit of 10 to the minus 14 ergs per second per centimeter square. And this survey will try to accomplish similar objective from the previous one, but shallower. But however, it will enable to detect soft X-ray sources to the longer distance due to the lower absorption towards the galactic anticenter. And in this plot, it shows the distribution of such soft X-ray source populations in the galaxies, and the sign shows the sum. And you can see many of these population are towards the galactic anticenter. And so another science area like our working group cover is the globular clusters. And this table shows the Chandra coverage of the galactic globular clusters. And about 10 globular clusters have exposures up to 100 kilosecond, and only 5 of them have exposures up to 300 exposures. Only with such a long integration, we can detect faint X-ray sources populations covering the range of luminosity in the range of 10 to the 29 to 10 to the 30 ergs per second. And this population includes the quiescent black hole X-ray binaries and millisecond pulsars. And so these with excess tenfold of exposures, where many more globular clusters will be mapped in with as deep as those that in 47 Ptak. Here shows an example of the simulation with access simulation on 47 Ptak with only 10 kilosecond, where the source are from Chandra observation as deep as 500 kilosecond. And it is also important to note that besides Chandra, only access and maybe links will have the ability with the efficient angular resolution to push the globular cluster science forward in the near futures. And I will leave my talk with a summary here. And we also have a great poster with an overview of broader science cases. And I will take any questions. Thanks.
So why don't we just start with the next talk, and then we can. So our next talk will actually be switching to the detectors with Eric.
All right, thank you very much. I'm going to tell you a little bit about the design and the technology behind the detector system for AXIS. And my name is Eric Miller, and I'm the focal plane lead on at Massachusetts Institute of Technology. Of course, this relies on a large team of people who are working on the design and working on demonstrating and developing this technology. The groups listed here include a group at the MIT Kavli Institute. This is led by Mark Bouts, our colleagues at MIT Lincoln Laboratory led by Chris Leitz, and a group at Stanford University led by Steve Allen and Sven Herman. And altogether, these three groups are responsible for the detectors themselves and the analog electronics system that goes with it. And then there's a group at Penn State led by Abe Falcone, who are working on the digital electronics. I do want to point out that all of this work has been funded over the last several years and continues to be funded in the present day and the future by NASA through both APRA and SAT grants. So Chris showed this slide of the requirements in his talk at the beginning of this session. I just want to bring it up again by pointing out that while the PSF is exquisite, the effective area is very high, the field of view is quite good, and the bandpass is quite broad, any one of these requirements would actually be pretty easily met by existing technology. The real challenging part for the axis focal plane is when you combine all of these things. And there are several challenges that that produces. The one that I want to stress is probably the most challenging is that this combination of PSF and effective area and also the large field of view requires a very fast readout rate, a very fast frame rate. And so in order to avoid photon pileup, we need to read out at least 5 frames per second. And so the requirements we have in order to meet, or the requirements on the detector system in order to meet the science requirements are actually pretty similar to the performance of the CCDs in running on Chandra and previously running on Suzaku in terms of their size, quantum efficiency, noise, and spectral performance. But we need to run about 20 times faster than Chandra, and preferably even faster than that. Okay. So before I get into talking about how we're going to meet those challenges, I do want to tell you a little bit about the design. So this is the design of the camera. This is the front end, including the detectors and the analog electronics. And so you can see some renderings of our camera assembly, renderings of the front end electronics box. And we also have a rendering of the focal plane. The focal plane consists of 4 detectors. They're shown by those little blue squares in the rendering in the lower left. These detectors are MIT Lincoln Lab detectors. Each one is a frame store backside illuminated CCD with 8 readouts. Not actually too different from the CCDs that are running on ASIS, except for some key differences, which I will get to. We have about 8 megapixels total. The pixel size is the same as the ASIS CCDs, 24 microns. The key advances over things like ASIS and XIS and Suzaku are the frame rate, which we need to be at least 16 times Chandra, preferably something more like 70 times Chandra for 20 frames per second. And in order to get into the higher end of the band pass, they need to be twice as thick as the CCDs that are flying on Chandra. And again, they need to be back illuminated also. So if you want more information about this, come see my posters in the instrumentation session 103. Okay. And so we do have a detector prototype. So the CCD is being developed by MIT Lincoln Lab and tested by our labs on campus at MIT. And so what I'm showing over on the right, this is an actual photograph of a prototype that we have currently running in the lab. And there are 2 technical advances that Lincoln Lab has come up with that really make this possible and make us able to run as fast as we can and meet those performance requirements. Okay, and these all come down to essentially being able to transfer the charge very quickly out of the CCD. The first one is a change in the way that the transfer gates are designed. If you think about a CCD, it's this bucket per grade charge transfer. We need to do that very quickly. And so I can, again, explain this a lot more in my poster, but the new design from Lincoln allows us to do that quickly with very low voltage swings. And so we can operate at at least 5 times, 20 times faster than ASIS for about the same amount of power, which is a huge breakthrough. Lincoln has also designed new on-chip amplifiers, which again, allow us to read out very quickly at low noise. And so the results from this first CCD, I have a little inset here which shows the spectral resolution at 6 keV, and we're meeting our requirement with a lot of margin there. This is from a front side CCD, and this just gives you, on the left here, this gives you a little bit of background about what this CCD is. It's actually the same number of pixels and the same pixel size that will fly on Axis, just a different layout. But at the rate that we're running it, that produces a spectrum that's equivalent to 7 frames per second. Now, this is front side illuminated. We need to use a backside illuminated in order to get that really good soft performance. So please come and see these posters for some backside illuminated CCD testing results, because that is underway right now. All right, so we're well on the way to having a CCD that can get out a low noise signal at the frame rate we need. There are other steps in the chain, however, in order to turn that into a nice event list that you want to look at. And a very important one is being able to amplify that signal so we can get it into our front-end electronics box, which is sitting a foot or 2 away from the CCDs. And so our friends at Stanford are working on developing what we've termed the MIT CCD readout chip. This is an ASIC-based external amplifier. It sits off the CCD, but very close to it. And this has 8 analog readout channels that all operate in parallel to match the 8 readouts. So we have one of these per CCD. And in that little picture over on the right, you can maybe see that orange square. That is where the ASIC will eventually go in this package, but that shows you the size of the ASIC. That thing replaces all of the discrete electronics that are shown in those 2 purple boxes. And so this really gives you 2 advantages. First of all, it's just a much smaller footprint, so you can put this into a flight package with much less problem. Also, those discrete electronics require a lot of power, and so this ASIC requires 10 times less power than that. We will be testing this with the CCD in just a couple of months. But the testing that's been going on at Stanford is shown in this inset here. This is showing waveforms of the signal input, both input and output in the ASIC. And you don't really have to understand what's going on there. These are just voltages. The key here is that the voltage changes are very quick, and the tops and the bottoms of the waveforms are very flat. And this is also running at 5 megahertz, which is actually considerably faster than our requirement. So in addition, we do need some development of front-end electronics that will do this fast digital video waveform capture. And so we're working on that as well. So if you want more detail, please see these 2 posters by Ken Moy and Peter from Stanford, also in the instrumentation session. All right, and the final piece of the puzzle, once we have that digitized signal, that turns out to be far too large in order to send down to the ground. And so we take those digitized pixel images, which are coming out at the rate of about 2 gigabits per second, and we send them into what we've cleverly called the back-end electronics. And this does essentially the same thing that similar electronics on ASIS have done for almost 24 years, which is to reduce those large images into a set of event candidates with some summary information about each of those. That's what goes into the event list that you all know and love. Again, these algorithms are not necessarily new, but they just have to be run at a much faster rate than existing instruments can do. So our colleagues at Penn State have been developing for the last couple of years this FPGA-based event recognition processor. And so that's what we will employ on Axis. And this should reduce that 2 gigabits per second by a factor of 10,000 and allow us to easily fit the data we need into our telemetry limit. In addition, the backend electronics will have a transient alert monitor, and this really is key for Axis' success at being a transient finder and alert telescope. This simply picks off that event list and detects changes in the rate compared to onboard source catalogs, which we can constantly update and then triggers an alert. This is based on a lot of development that the group at Penn State has done for the transient alert monitor that was proposed for the Athena WFI science projects module. Now, that particular piece of hardware did not go forward, but we can capitalize on all of the work that's gone into developing that for this. And Abe will be at this meeting, so if you're interested in any information about this, please track him down, but you can also see these references. All right, so just to summarize, what I want you to take away from this is that the Axis camera is really a pretty simple design. It's based on a lot of heritage, but it does have to run much faster. However, we're well on the way to solving those technical problems and having a really nice instrument that we can use for Axis. And if you want more information, please come and talk to us. A lot of these posters are in the instrumentation session. We'll be happy to tell you more. So, thank you very much.
Okay, so time for a quick question.
Yes, what is your current TRL, and do you think your APRA and SAT funding will be sufficient to get this TRL thing?
The question to the answer to the second question is yes. That was the goal of the APRA and SAT funding. I plead the fifth on the current TRL simply because we have not had a TRL assessment, so I do not want to say a number that has no basis. But we have we do have a TRL, a plan to get to the TRL we need to be when we need to be there.
Okay, so let's move to the last speaker in the Ptak on community involvement. Hey, Andy.
Okay, so I'll be quick. I'm Andy Ptak. I'm at NASA Goddard, and I'm also the Access Project Scientist. Let's get one. Okay, so in terms of community engagement, we formed science working groups. That was an open call that I think was pretty well received. We got a lot of people. I don't remember off the top of my head how many exactly. But that's the basis of our science teams that are now going to be helping write the proposal. There's a monthly seminar series that started around the same time last spring. All the talks from the seminar series are recorded and go onto the our YouTube channel. So definitely check that out. Plus special sessions like this are being recorded and you can look at them later on the YouTube channel. We have a Twitter handle, I guess is the right term for it. That's thanks to D Foord, who you heard from earlier, and there's the handle for that. And then of course, all pro proposals must have a web page, and so that's our web page. So in terms of simulation tools, the special responses for Access are on our website, and then you can also do end-to-end simulations. So there's two main tools for this that are popular, SimX from CFA. You download that from CFA itself, but then the configuration files are on the Access website. And then 60, which is developed in Germany and is the official simulator for multiple missions like Rosita and Athena. Again, you download that, the actual packages for 60 itself, and then here are links to the instrument-specific data you need for doing Access simulations. So an interesting aspect of this is that Moritz Gunther from MIT spent some time doing more precise modeling of the PSF. So the standard thing to do in tools like this is just to have a simple Gaussian PSF. And I should emphasize that the science case we're baselining is only going to be assuming a simple Gaussian PSF because we don't know what the final PSF shape is. But as most people in this room probably know, a typical X-ray telescope doesn't give you a Gaussian. It usually gives you that's something that's more like a Gaussian and a Voigt profile combined. So what Moritz did is he scaled, or he essentially fitted the Voigt, the tail of the Chandra PSF with a Voigt function, and then generated PSF images to use with Access. So if you have science where you want to play around with having a more precise PSF, the files in that second link there under 60 will let you experiment with that. And that could be relevant for obviously for lots of different science. But again, we're not going to baseline that in the proposal. This is just showing you what's in the response files that was mentioned in the previous slide. So and again, you can just see the improvement over what I'd like to call all current X-ray missions, even though CRISM hasn't launched yet. It will hopefully in a few months. So this is hopefully a good comparison against all current imaging CCD-like X-ray detectors right now. I guess, sorry, Swift's not on there, but it should have been. And so you already saw a lot of these posters. Most of the talks ended with, of the science topics ended with their list of posters, but just showing we have a decent number here. Yeah, I guess you could take a picture of that, or you could just look for Access in the program online and you'll find these, but just wanted to mention there's plenty. And there's a probe special session on Wednesday. And of course we have Chris giving a talk at that. And I know nobody likes seeing an org chart, but my point here is just, this is just a science part of the org chart. And it's just showing that a lot of the people here are at the meeting. So definitely come talk to us. And then let's, and then.
Okay, so we have a couple of minutes for any questions about Access. I think I'll do the last. Oh, go ahead.
Sorry, I don't want to go back there for you. What are you doing with the vaccine?
The baseline plan is to use this molecular beam epitaxy MBE treatment that Lincoln Lab has developed. And so part of our VI tests now are to verify that that treatment. But a couple of years ago, we had a similar device that was similarly treated, and it showed very good performance as well. So it's a different process than was used on ACES, and it's a different process than the chemosorption process that was used on Suzaku as well, which had actually exquisite cell spectral resolution for a CCD instrument. But we're hopeful that we'll be able to achieve something very similar, if not the same, as Suzaku.
Okay, thank you.
Any final questions?
If, like the instrument specifics had also been like, discussed and sometimes changed, like the PSF size has been discussed, and also recently the field of view has been changed from square, to a circular region, so all of that, like, is, being discussed and, like, and how can we, like, like join the discussion and how to like achieve different sign. Yeah.
Thanks, yeah, so, as you, in basically the beginning of the year, sort of December through to January, there was a shift in response matrices and also field of view. What you saw there was what happened when we took the engineering to the next level. We saw sort of a bit more reality biting in. And I think from the point we are now, we have a consistent closed design. So I think there shouldn't be any further evolution of those parameters. Let me just take the last word to thank everyone for their attendance here. As multiple people said, most recently Andy, you know, if you see any of us around, feel free to stop us, ask about access. And if you have ideas and want to get more involved, then just please approach us. You know, we're all very approachable, very friendly. So even if we're in the middle, you know, if you look busy, just break in and just talk to us. So thank you very much for